All right, hello everyone and good afternoon. My name is Susan Bates, and on behalf of KUKA Robotics, welcome to the Understanding Robot Absolute Accuracy webinar today. Webinar will be presented by our senior engineer, Hussein Walid, and everybody's microphones are already muted, but if you do have a question, I will ask it that you type it into the chat area, and please make sure you do it to the entire audience so that everyone else can see the question that you're typing. So without further ado, Hussein, I will leave it to you, sir.
Thank you very much. My name is Hussein Walid. Like Susan said, I'm a senior engineer at KUKA. I've been with KUKA for more than 25 years. My main interests are in robot performance and advanced applications, including cobots and mobile robots and so on. Today, I'll be talking to you about robot accuracy, definitions, source of error, standards, calibration, and more importantly, some practical considerations. If you have any questions, like Susan said, please enter them in the chat and make sure to address them to everyone so that everyone can see the questions. And every now and then, I will ask Susan if there are any questions, and we'll answer them as we go. Definitions. Repeatability, the ability of the robot to revisit a position. You command the robot to go position, whether it's the right position or the wrong position, doesn't matter. You ask it to go to that position again multiple times, and then you measure how much deviation is between in that area, and usually you consider 3 sigma as a measure to define that repeatability. There are 2 kinds of repeatability that we talk about in robotics: the unidirectional repeatability. The position is approached from the same direction, and the multi-directional repeatability. The position is approached from different directions. And as you can imagine, the unidirectional repeatability would be much better than the multi-directional repeatability, mainly because we take care of the backlash when we use only unidirectional repeatability. But when we're using multi-directional repeatability, then we see the backlash in some of the axes. In my experience, the multi-directional repeatability is about twice the unidirectional repeatability. So that's one thing that you need to keep in mind when you're asking about the robot performance. You want to ask about the repeatability, then you ask about unidirectional repeatability and multi-directional repeatability. Accuracy. Accuracy is the ability of the robot to attain a commanded position. In some definitions, you see definitions like the ability of the robot to attain a position that it has never visited before, and that is wrong. It's just the ability of the robot to attain a commanded position, whether it has attained it before, visited it before or not. And it is defined as the difference between the commanded position as measured by an outside measurement system and the attained position of the robot, or the mean of the attained positions by the robot if we command it to go multiple times. You've all seen this before. The and accuracy versus repeatability. They are completely different measures of the robot uh, performance. In my opinion, they should not be completely different from a statistical point of view, but in this here, you can see a robot that is repeatable and accurate. In here, you can see a robot that is very repeatable but not accurate, far from hitting the commanded position. In here, you see a robot that is neither accurate nor repeatable. And in here, you see a robot that is accurate but is not repeatable. Again, in my opinion, this robot is not accurate because just because the mean position coincides with the commanded position does not make it accurate at all, and nobody in the world would see this robot as accurate. But accuracy and repeatability are measured differently and are assessed differently, and we have all four rows of the truth table, if you will. Again, to emphasize what I was just saying, all these robots are accurate if we stick to the definition. This robot is right on, but this robot, hits over here and then hits on this side. But the mean is right on the commanded, which makes it accurate. This robot is, hits all over the place, but the mean again is very close to the commanded, which makes it accurate. And this robot hits just on the outskirts of the target, but if we calculate the mean, then it's very close to the commanded, which makes it accurate. But like I said, nobody in the world would consider these robots as accurate, but that is the definition. Thankfully, robots are not just statistical entities; they are mechanical entities, and usually the repeatability is many folds smaller than the accuracy, whereas the repeatability is in the ranges of 0.02 millimeters to 0.1 millimeter. The accuracy is in the range of who knows, for a calibrated robot could be 0.5 millimeter to if a robot is not calibrated, could be 10 millimeters, who knows. Any questions so far, Susan?
I don't see any questions in the chat thus far. Again, if you have any questions, please put them in the chat and please ask them to the entire audience. So none so far.
Okay. And then we have the path performance. Standards deal with the path and trajectory separately. Some of you might know that there is a difference between a path and a trajectory. The path is the signature of the TCP, the tool center point of the robot in the 3D space. The trajectory is the signature of the TCP in 3D space along with the time that it gets there. In other words, it's the path plus the velocity, not only where the robot is, but at what time the robot is. So usually the standards will deal with path accuracy, path repeatability, velocity accuracy, velocity variation, and so on and so forth. When sometimes all you care about is path, and sometimes you also care about you care about trajectory, and sometimes you care about path and velocity. As long as you're maintaining a constant speed along the path, like if you're doing gluing or something like that, then that's all you care about. Standards. We have the ISO 9283, which is pretty much the de facto standard for robot performance, and it speaks about all kinds of performance, accuracy, repeatability, overshoot, path accuracy, path repeatability, and it defines very specific procedures for measuring all of these performance metrics. At the same time, it leaves some leeway for the tester to define, the load, to define the speed, to define where the test is done in front of the robot, and so on and so forth. The RIA equivalent of the ISO 9283, and they're pretty similar, is the 15051, which deals with the static performance, and the 15052, which deals with the path performance. These standards can be bought from their organizations. They're not free. You can just Google and download them. Again, talking about the IsoCube. The standard defines a cube in front of the robot where all the measurements are going to be done. The cube size obviously depends on the robot type, and the measurements are done with specified loads and speeds. Obviously it's impossible for standard to list exactly what that cube is for every robot type or every robot reach or something like that. So that's left to the person who is doing the test to find the best place to put that cube. And obviously any numbers that you see for repeatability or accuracy are only applicable to that cube if the manufacturer specifies that the metric is with respect to, let's say, ISO 9283. So it's not going to be all over the workspace of the robot. Any questions so far?
None that I see.
Okay. Where do errors come from? Why aren't robots spot on when it comes to accuracy? Joint offsets, discrepancy between mathematical and actual zero position. The robots, the articulated robots, are modeled based on the H parameters, the Navet-Hartenberg parameters, and those parameters define frames for each joint and link. And they assume a zero position for each joint to describe the kinematics of the manipulator. When the manipulator is manufactured, those actual mechanical zero has to correspond exactly to the mathematical or the model zero position of the robot to be accurate. Obviously, that is impossible to be 100% on equal, and those errors will um, affect the accuracy of the robot. Another source of error is the geometric parameters like the link lengths, the twist angles, etc. When you build the robot, you build each link within some geometric tolerances. It's not going to be exactly like you modeled it in your CAD system and so on. And those geometric parameters, the geometric discrepancies will affect the robot accuracy. Non-geometric parameters like joint flexibilities, like your base tilt. Joint flexibilities refer to the fact that your gears are not 100% solid. They act like a spring. When you push on the robot, those gears will give. And obviously, just with the weight of the links and then the weight of the tool that you're holding with the robot, that's going to affect that position. The base tilt refers to the easiest way to explain the base tilt is just imagine a person standing up straight, and as you move forward or bend a little bit forward, then you can feel that your heels are lifting off from the ground. And the more you bend over forward, the more your heels are going to, to move up from the ground. The robots are no different than that. When you stretch the robot out, the base of the robot is gonna tilt a little bit. And there were studies that were done that show that the non-geometric parameters, like the link, like the joint flexibilities and the base tilt, are the major factors in robot accuracy problems, more than the joint offsets, because those are very close usually, and more than the geometric parameters like the link lengths and the twist angles, because those are usually small because of the tight tolerances to which the robot is built. Another factor that affects robot accuracy is the environment, temperature, humidity. The robots are made out of metal, usually steel, and the harder the metal, the more it expands and affects the accuracy. And then you have measurement factors like nonlinear encoders and resolvers and so on. No questions still?
No questions at this time. Again, if you have questions, please type them to all the audience in the chat area.
All right. Calibration. How do we make the robot, if the robot is built, it's built as, the way it is built. Now we want to make it more accurate. We make it more accurate by calibrating it, and meaning we're going to find out what it is actually and use that information to in forward and inverse kinematics of the robot. To do that, we need a calibration model, a kinematics calibration model. The model must be realistic and it must be observable. What do I mean by realistic? Imagine a sine wave. If you have a sine wave and you model it as a line, you're free to do it, but you're not going to get far. So when for example, joint flexibilities in the robot, I can model them as a spring, a linear spring. But if that's not what they are in actuality, then I'm just wasting my time. It has to be, the model has to be actually, almost what the robot, how the robot behaves. And that can be measured. The model can be measured. You push, for example, for the joint flexibilities, you push on the joint with known torques, and then you see how much it moves, and from there say, okay, yeah, this is pretty linear, and if it's pretty linear, then I can model it as a linear spring. If it's not linear, then I need to model it as a nonlinear spring, and so on. That's what I mean by it has to be realistic. It has to be observable. The observable means that I can identify it from measurements. Let me give you an example for that. Let's say I put I'm trying to identify the last lane, the last axis on the robot, and I put a load on it, and that load has a CG that is exactly on the axis of the robot. What that means is it doesn't matter how much I excite that axis, I will never see a torque on it. And if I never see a torque on it, then I cannot observe the flexibility on that joint. So that's what I mean by observable. And for calibration, we also require an external measurement system. You cannot calibrate the robot by itself. You cannot. So you need an outside and external measurement system. Lately, before, all kinds of things were used, like put the robot on, attach the end effector to a fixed point with a spherical joint, and move the robot around in a servo mode and measure, with then some cameras were used, but lately most calibrations are done using laser trackers because they are very flexible, they are very accurate, and the external measurement system must be many folds more accurate than the desired accuracy. If I am looking, I'm measuring a robot, and I know that the calibration, the robot can be 0.5 millimeters. I cannot measure that with I cannot measure the robot with a measurement system that has a 0.5 millimeter accuracy. That's ridiculous. It has to be at least 10 times more accurate than what I'm looking for.
Hussein, there's a couple of questions. Can I ask?
Yep, sure.
The first question was, where can we find the robot accuracy information in the robot data sheet? The repeatability is listed, but I cannot easily find the accuracy.
The accuracy is actually in there with the data sheet. Includes the repeatability, the static accuracy, and the dynamic accuracy. If you cannot find it, then let us know. We'll send it to you, and we'll point you where to find it. I'm talking
Okay.
about KUKA. I'm talking about KUKA.
Okay, next question. In slide 12, you mentioned that the accuracy of the cube depends on the robot type. Can you elaborate on that?
Sure. So when you do your test, you define a cube in front of the robot. And I did not say the accuracy of the cube. I said the size of the cube and where the cube is. So obviously, for a small robot, it's going to be a small cube. For a large robot, it's going to be a larger cube. Um, and that's defined by the tester will define where the cube is, and also by the manufacturer if the manufacturer publishes ISO standard metrics like repeatability and accuracy. Normally, what needs to be done is when you do your report, that cube has to be included in the report along with what points were used from the cube and what load was used and what speeds and so on and so forth.
All right, there's two more in here. Why is calibration needed for the robot?
Okay. Yes. So calibration, when, like I said, there are all those sources of error that we can control, meaning the geometric sources of control and the. Let me go back. So the joint offsets, the geometric parameters, and non-geometric parameters, those we can control. We can measure and we can build a map and identify them and use them. When a robot is made, like I said, when a robot is made, there are nominal values for, let's say, for example, for the link lengths between one joint and the other. That's based on the design of the robot. The joint flexibilities, the gears have flexibilities. We don't know what those flexibilities are because they will be different from one gear to another, and not necessarily for whole type of gears. So with those sources of error, no accuracy is guaranteed beyond a maximum. So, for example, a robot that is not calibrated could have an accuracy of 5, 6, 10 millimeters. Who knows? Depends on the robot size and so on. And as you can see, if you do an error budget from the base of the robot to the tip of the robot, with the robot stretched out, you can have much bigger accuracy issues. So the goal of the accuracy of the calibration is to identify the real link lengths and twists. If there are any discrepancies between the zero offsets between the zero angles, mathematical and mechanical, and so on, and identify the flexibility in the joints and account for the base tilt and accounts for the twist angles and so on, to actually use the real values from the robot to make the robot accurate. So when we ask it to go to a position, instead of going there within 10 millimeter potential error without a calibration, or 2 millimeter or 5 millimeter, depending on the robot size and so on, and position in the workspace, then we can go there with 0.5 or even less error. Next.
Okay, I have three more questions. They're coming in
Okay.
now. Does the calibration have to be done at the final place of the robot?
So as far as KUKA is concerned, you can buy the robot calibrated from factory, and what that means is it's it's calibrated with full load. So if you're buying a robot that is 240 kilograms, then it's calibrated with 240 kilograms, and it is calibrated in the whole workspace, meaning in front of the robot, the side of the robot, behind the robot, etc., etc. Um, in a lot of applications, that's good enough. That's perfect. In some applications, the um, a customer would buy a robot that's 300 kilogram robot, but they bought it just for the reach, and instead they're going to be using 50 kilograms instead of 300 kilograms. In that case, and they want to, it's a really accurate application. In that case, we can calibrate that robot with the 40 kilograms, and let's say only in front of the robot, because that's where the application is done. And in that case, you can get much better, um, much better accuracy results. You can get up to down to 0.2 millimeter accuracy. However, and this is a big however, KUKA only guarantees what is published in the data sheet, but we can reach much better um, accuracies than what's published. And this accuracy, this calibration, the what we call it custom calibration, can be done at the KUKA facility, or can be done here in the US or in Canada, or can be done at the customer site.
Okay, do the accuracy tests take into account the difference between a quote-unquote cold robot that just started up versus one that has been moving for a while with warmer gears and oil?
Usually the robot is warmed up before we do the accuracy, because no robot works when it's cold.
Okay, how can we check the calibration errors in the robot once the robot is calibrated?
Um, so I don't know exactly what they mean, but I'll answer both scenarios. So after we calibrate the robot, we do a validation to measure the accuracy. If you want to, once you receive your robot, you can also do a validation, but that means you have to have an external uh, measurement system. You have to know where the base of the robot is and where the TCP is. You can either do it by yourself, you can hire someone to do it, or you can get KUKA to do it, but that's doable.
Okay, do we need a complete and perfect accuracy during the calibration process, or can we proceed it as is?
Okay. Complete. I
Do
don't
we need a
understand the question.
complete and perfect accuracy during the calibration process, or can we proceed as is?
I if they can please elaborate. I do not know what that means.
Okay, so I'll wait for this person to elaborate, and there's another question in the
Okay.
meantime. Can you
Yep.
explain the need for base calibration?
The base calibration.
Can you explain the need for base calibration?
Okay. We'll talk about that later if they're talking about the base as in the frame or user frame. Um, Not to be confused with the base tilt that I was talking about. By base tilt, I was talking about the physical, uh, hunk of steel of the robot at the base of the robot. But we'll talk about that later.
Okay, no other questions at this point. I'll wait till
Okay.
this person asks again.
Okay. All right. So what does calibration give us? Accuracy improvement from 3 to 5 millimeters mean to 0.5 to 0.7 mean. And like I said, even though KUKA publishes what it publishes, depending on the robot, 0.7 mean usually, we can get much better values with custom calibrations. When do you need accuracy? You need accuracy especially these days, in a lot of applications, including material removal, additive manufacturing, dispensing, like gluing, inspection, load sharing. By load sharing, I mean this figure here, for example. I have two robots that are sharing a load and moving it around. And obviously, if they're not accurate, then they're going to be tearing that load apart, figuratively. So you need them to be both. You need to be accurate. First, themselves accurate each, and then you need accurate base measurement between the two robots. Sometimes you don't need accuracy for the application itself, but what you need accuracy for is for exchangeability. Let's say, I have a production line with 200 robots, and I don't want to lose time if I am replacing a robot. So by having absolute accurate robots that are placed with a repeatability on the floor, I can take a robot out, put another robot in, and because they are absolute accurate, both of them, then I don't need to change and touch up points in between. Now, if I don't do that, then the difference between the first robot and the second robot is 2-3 millimeters. Then I will have to touch up all the points, even though the accuracy is not needed. But to exchange the robots, it makes it a lot easier. Any questions?
I do not see any more at this time.
Okay. Now, practical considerations for accuracy. Number one, start with a good foundation. Good foundation, first of all, means literally, because a flexing floor is a recipe for disaster. If your floor moves and the robot base moves on that floor, then you're gonna have headaches. You need to select the right robot, right accuracy and repeatability specifications, and the right duty cycle capability. Depending on how the robot is going to function, is it gonna get warmer and warmer as it does its job. You want to select also the right tooling. You can't have an end effector that moves when you're looking for good accuracy. It's team sport. A lot of people only look at the robot, from the base of the robot to the flange, but that's only one part of the error budget. That's only one part of the accuracy equation. You also need your base. If you're working in a base, you need to calibrate your base or measure your base properly. You need to measure your TCP properly. you need to measure if you're you know, on a linear rail or any kind of kinematic system that is beneath the robot and the robot is on it, then you need to calibrate that system to the base of the robot. So you have a whole kinematic chain from world to the linear track, to the robot base, to the robot flange, to the TCP, to the base. And if you want to squeeze, we'll talk about that later, but if you want to squeeze as much accuracy as you want from your system, you're not going to rely on traditional ways of, you know, the 4-point method for the robot, for the TCP, and the 3-point method for the base. You want to rely on more advanced things like, for example, use a laser tracker to measure where everything is with respect to each other. An accurate machine is a thermometer. Heat can cause inaccuracies of up to 1 millimeter. If your robot is constantly accelerating and decelerating, it's gonna get hot. And the hotter it is, the more the links will expand, and you can get into you know, up to a millimeter deviation. So you need to either control the temperature by, you know, using fans on the robot, on the motors, or putting the whole thing into a temperature controlled room and so on, or compensate for the temperature. For example, there were applications where we had to characterize the error to the temperature of the motors, and we put in compensation methods there to you know, read the motor temperature and compensate for that. So again, an accurate machine is a thermometer, and you have to measure the temperature if it's area of concern and compensate for it. The sweet spot. Robots, just like people, do not like to be stretched out. If you're looking for accuracy and tight tolerances and tight accuracy, you don't want to be working with the robot stretched out. So you need to devise some strategies to keep the robot in the weak spot. For example, have a turntable in front of the robot so that the robot is always working in a relaxed position. Sharpen your tool. You need an accurate tool definition. You cannot, like I said earlier, you cannot rely on, for example, the 4-point method to measure your tool. That's, you know, sometimes that's not accurate enough. You want to be using, for example, a laser tracker or something like that to measure your tool. Same thing for the base. If you're working in a base, you probably want to you know, use more advanced methods to do that, rather than use the 3-point method where, you know, with your eye you're going in there and so on.
Can I ask a question?
Yeah.
Does the compensation, could it be modulated as a linear function, or is it something more complex?
It really depends on, you have to, like I said, you have to characterize it. So in our case, in one of the applications, I measured the deviation with the laser tracker in 3D, and correlated that to the motor temperature. and in that case, it was not very linear. So what I had to do was have a table, a lookup table, and just interpolate between the closest points, and that worked very well.
Okay, we have a couple more questions that came in.
Sure.
Is there any documentation on how to do the calibration with a laser tracker, and can it be done by KUKA?
The calibration is done by KUKA. But the difference between doing, so for a KUKA robot, the difference between doing the calibration by KUKA and doing the calibration by an external company, KUKA, when KUKA calibrates the robot, we take those values, we take the identified model, and we use it for the kinematics of the robot inside. When you use an external company to do the calibration, they cannot do that because you don't have access to the internals of the controller. So what they do is they do what's called command shaping, which I'm going to talk about in a couple slides. Do the command shaping where, in terms of, oh, this is where I need to go. I'm going to fake it and ask it to go over here to make it go to where I need it to go. What that means is you have accuracy at the start of the motion, you have accuracy at the end of the motion, but you don't have accuracy in between. Whereas KUKA, because it uses the identified model in the kinematics, then you have accuracy at the start of the motion, you have accuracy at the end of the motion, and also in between. So your line will be more accurate than if you use an external calibration with command shaping. More questions?
All right. And last question for right now is, how would one use a laser system to measure the TCP?
Okay, so it depends on what the TCP looks like, what the tool looks like. For example, one way of doing it is to measure. Let's say you have features that you can measure, that you can relate to the TCP. Let's say, for the sake of it, that the TCP is at the one of the corners of a block of then one way, for example, would be to measure the flange of the robot, because I know exactly where the center of the flange is. I know exactly what the X direction is. So I would measure the flange of the robot, put the TCP, put the tool on the robot, and then measure that block, and then calculate where that corner is with respect to the flange. Obviously, if the tool is heavy, then when you put it on the robot, then the robot's going to sag a little bit. So what you want to do is you want to attach, 3 points or 3, on the flange that you can measure before and you can measure after to refer everything back to the flange itself. Another way would be, let's say, for example, you're measuring a spindle, a tool at the end of a spindle. So again, you measure the flange, then you measure the cylinder, you measure the tip of that cylinder, which is your tool, and that would be, and then you calculate the orientation and at the location of that tip. So it really depends on what the tool looks like and what features I can measure to deduce where the TCP is.
All right, there's a bunch more questions that came in, so we'll try to get through these quickly. What is the impact to load
Can
variation?
I just finish? Can
Sure.
I just finish? We only have
Absolutely.
Yeah.
Then
So
we'll do the question.
yeah, and then we can go through the questions. And it's okay. It's okay for me if we go over the time. That's okay. Um, so you want to carry the right load. Not only carry the right. So you need to know what load you're carrying on the robot, and you need to let the robot know what load it is carrying so that it can compensate for it. Okay. Um, if you're considering um, really, tight accuracy, then I would recommend to use a higher capacity robot and for than the load that you are be using. Let's say if I'm only carrying 3 kilograms, then I would consider using a robot, a 16 kilogram robot, for example, so that it's going to be a lot more accurate that way. So always use the right load data, calibrate with the application load, and consider higher capacity robots for a better accuracy. Ask the correct questions. Should I even care about accuracy? We've had customers asking about accuracy, and then when we investigate, they do not need accuracy. What they meant was repeatability. That's all they need for their application. What is the multi-directional repeatability? The manufacturer publishes 0.05 millimeter repeatability. Is that unidirectional or multi-directional? I don't care about unidirectional. No robot works in unidirectional repeatability. What is the maximum accuracy error in my intended workspace, and not not just the ISO cube. Does the stated accuracy cover the whole workspace again, or just the ISO cube? What is the path accuracy of my intended application? What is the velocity accuracy? Do I even care about velocity accuracy? If I am doing dispensing and things like that, then yeah, I do. What happens if when the robot becomes out of tolerance? I've been using the robot for 10 years. Now my accuracy is down. What happens? Do I need a new robot, or can that robot be recalibrated? In KUKA case, if the robot is still mechanically sound, and after 10 years, usually KUKA robots are still mechanically sound, then it can be calibrated again. What happens if I crash the robot? Well, is it gonna lose its accuracy forever? No. Again, if there's no big damage, then it can be repaired and calibrated again. How do the process forces influence the robot accuracy? Usually they do. Um, so that's a question. Am I going to be, using process forces? Like, am I milling? Am I using the robot to drill and things like that? That's going to affect my robot accuracy, and I need to ask the manufacturer those questions. Now remember, a robot, an articulated robot, is pretty much a slingy. It's a it's like it's like a spring. It's not going to be replaced, for example, a CNC. So sometimes you need to give it a push by using external measurement like vision or tactile sensing or laser tracker in a visual feedback form to place the robot exactly to where it needs to be. But sometimes you still need command shaping. For example, um, if I need to place the robot to 0.1 millimeter, that's not going to happen by just the robot. So sometimes what we do is we put targets on the robot and targets on the part, and then we measure both, and then we compensate until we get them to where we want them. But these usually are very expensive applications that can actually afford to have a laser tracker in the loop or vision system or something like that. Sometimes you need to do command shaping. An example would be, I want to do a perfect circle to within, let's say, 0.0 something millimeters, and the robot cannot do it on its own. Sometimes, if it's something that's going to be done over and over again, the same thing, then you would cut, you would measure, you would shape in a CAD system or something, the robot to go over or under the radius to actually get it to do what you need it to go. But a robot is not going to replace CNC. You have to be aware of that. All right. Questions?
Okay, this one's sort of a two-part. What is the impact to load variation on accuracy? Would less load mean more accurate? For example, the KR120 R3900, the accuracy rated on the datasheet is 0.7 millimeter. What will the approximate accuracy be with no load? So sorry, it's kind of a two-part.
Okay, so yeah, so let me answer that for KUKA. That robot is going to be, if it's calibrated, factory calibrated, then it's calibrated for 120 kilograms with 120 kilograms. If you put no load on it, then it's going to lose actually some accuracy. So if your intended application is to use it with no load, or 5 kilogram load, or 10 kilogram load, or 20 kilogram load, you want to calibrate it for that load. And as long as you are within, let's say, 20% of the load, then you're fine. But if you're intending to use it with much less capacity than a load that is 10%, 20%, 30% of the capacity, then you probably want to do a custom calibration with that load.
Okay, next, this is a follow-up question to the question about calibration with a laser tracker.
Okay.
So if we want an accurate path, is it better if we stay with a KUKA factory calibration?
If you want an accurate path, again, same thing. But factory calibration is going to be done with the maximum load. If you want path accuracy with a much smaller load and much better accuracy, then you probably want to do a custom accuracy as well.
Okay, next question. Is it possible to activate the flexibility model on a non-calibrated robot?
Okay, let me see here. I don't know exactly what this person means. You cannot activate a because you cannot. It's part of the kinematics. We have another thing for flexibility, but that's for the path stabilization to reduce vibration and so on. But that's separate. But as far as calibration is concerned, is either everything or nothing.
Okay, next question. Any method to do calibration other than the 4-point method?
For the internally, no. But what you can do is, what some people do is, for example, with spindle, they start cutting They cut until they align the cuts, from one side and the other until they align the cuts, and then they cut from this side and from 180 and so on to calibrate their TCP like that. But that's depends on the application, what you have, and so on and so forth. And even the 4-point method is not always possible, because you don't always have a pointer or a point to use on the tool to do 4-point calibration. So it depends on the application. We are always happy to discuss your application and discuss how we can get the best out of the tool.
Yes, I realize it's 2:01 and we are unfortunately out of time. There was a few more questions. I'll have Hussein answer for those who want to stay on and hear those. This recording will be available on YouTube in the next couple of weeks. So there was a question if we were going to share this PowerPoint, but the whole session will be available on YouTube. Hussein, do you have time for a couple more questions?
Sure. Yes, I see people actually want in the room, but go ahead.
Okay, let's do one more. There are some documentation of how I can configure external loads attached to the link of the robot. For example, the hose management system. Is there a procedure similar, and is it normally done with the tool?
No, there is no procedure to actually measure the auxiliary load. You have to either define it from a CAD or something like that.
All right, I'm sorry. Unfortunately, we ran out of time. I will make sure for those questions who weren't answered that Hussein does answer those for you in an email. So on behalf of KUKA Robotics Corporation, thank you very much for joining. And we'll see you next time, folks. Thank you.
Thank you.
Industrial intelligence.